In our discussion of the electric field, we've been doing calculations to find the field at specific points. But as I mentioned earlier, the electric field exists all around the charges. So if I have positive charge and a negative charge, there's a field that exists all around these two charges. So this is just one line, but you're going to have field all over the place. And you're even going to have it on the back side of the charge. If these are the only two charges that exist, I'm just going to draw a line here and I'll put arrows. You're going to have some line that exists all the way around to the back. So these lines exist everywhere in space. We just can't think about it as existing at one point in space. We can determine the electric field at one point easiest based on the symmetry that we've been using, but if we wanted to find a point that's not within symmetry, well, that's a little bit harder to do. But we have to realize that these lines exist everywhere. Now, let's say that you have a charge of size Q and you have a negative charge of negative Q. Well, what will happen is that for all of the electric field lines coming out of the positive charge, an equal number of field lines will be entering the negative charge. So all the field lines will begin and end on positive and negative charges. Now, if I have a positive charge of 2Q and a negative charge of Q, Q can only accept a certain number of field lines based on its size, but that doesn't mean that the positive charge isn't going to have other field lines. Those field lines are going to go searching for negative charges and the charge of 2Q is going to have twice as many field lines as negative Q. If I have two charges that are positive, then the field lines are going to warp away from each other so that they don't touch. And the notes have has a better picture of this, but just try to draw it out here. So you're going to have this void in the center because the field lines are not going to want to come together. This point will be zero, zero electric field in the center. Now, another situation, if we have two plates, one has positive charges and the other plate has negative charges, it has to be the same amount of positive to negative charges. Because remember, field lines are proportional to the charge size. So I can only get so many electrons to match up with, or I should say, so many negative charges to match up with the positive charges on the plates. So the takeaway from here with all this information is that the electric field exists at all points. There's two ways of representing an electric field. And I'm going to put electric field strength. And that is longer vectors stronger field, or high density, basically cramming more and more into a smaller space, is a stronger field. And the amount of electric lines entering or exiting a charge is proportional to the charge magnitude or amount. Now, this brings us to our next discussion about electric field lines and what happens inside of conductors. So let's think about a sphere for the moment. And I distribute some, or I put some charge Q at this little location. Well, what's going to happen? Well, there's no charge here at the moment. I have a lot of charge at this little area. And all of the forces are going to push these charges around until I get to a point where I have charges evenly distributed along the surface. So they're going to, in fractions of a second, move along this whole surface until all the forces cancel out and everything is equally distributed along this surface. And when that happens, when all the forces cancel, which means that all of the electric fields cancel. And so there is no electric field inside conductors. If there was an electric field in here somewhere, that would force one of the charges to move closer to another charge, which would produce a force and an instability, and would cause all the charges to move that in such a way to cancel out the electric field. So there cannot be an electric field inside the conductors. Now we can take a situation where I have a sphere, and let's say a shell here, and I pop in a positive charge in the center. Well, this positive charge is going to have electric field lines coming out of it. And so when the electric field gets to this surface, it's going to attract negative charges. And it's going to repel positive charges. So the negative charges are going to exist or be placed on the inside skin of the shell, and the positive charges are going to be on the outer skin of the shell, and then these positive charges are going to have an electric field come out. But in this area, no electric field. In this center area here, in between positive and negative charges, no electric field. It all cancels out. Now, if I were to look at a very tiny differential area or differential volume, yes, I would see an electric field. But taken as a sum, taken out over the whole shell, all the electric fields cancel. And so because of that canceling, we say that there is no electric field inside of a conductor. Now, one application of this is very useful. Let's say that I have some plate with positive charges, and I have another plate with negative charges. And now let's say I put something in the center here that's made of some type of conductor, a box. Well, what will happen is that the electric field line will come to this inside box, and it's going to attract the negative charges along the surface. And the other side of the box is going to have positive charges, which will have an electric field line. But inside this box, there is no field. And this is an example of what we call shielding. Why would this be useful? Well, let's say that I have a piece of equipment that's very, very sensitive to noise outside. And I want to be able to analyze this box without noise. Well, what I do is I put this box inside of a metal box, and the metal box keeps this outside interference from affecting it. Anything electrical, the box will keep from going inside to affect my piece of equipment. This is used a lot in industry. They have special rooms that are built with metal casings that they can take equipment into and run tests without having any kind of interference from the outside. This also explains why, if your car is hit by lightning, as long as you're not touching the surface of the car, that you will not get struck by lightning. The charges get distributed over the shell of your car, and the electricity or the charge won't go through, and you can't be struck by lightning on the inside of the car. Now, if you touch the metal shell, touch the metal of the car, yeah, you could get shocked at that point. But as long as you're not touching the metal parts of the car, and the car gets hit by lightning, you will be safe inside of the car. This is the reason, the theory or the application of why you can survive a lightning strike on your car.